second session of the MAST summer webinar. If you were at the first session a couple of weeks ago, you learned all about how to make a mosaic image with HST data, and today's session is focused all on spectra, rainbows and the like. And so we will be getting into that. We're going to be going through a Jupyter Notebook tutorial for this webinar. If you would like to follow along, you are encouraged to do so at this URL link, timeseries.science.stscI.edu. You can log in with your Space Telescope account, and then you'll be able to code along with me live and follow along. You don't have to follow along live. This is just if you want to. Everybody learns in their own way. So if you feel like you would benefit from that interactivity, please do so, but it is in no way required. I'll give you guys just a second to log in for those of you that are interested in following along. And when you first log in, you should see a welcome screen that looks like this. Welcome to Tyke. And then to get to the notebook that we're going to go through today, you can click on this little file browser in the top left corner. Go to the References folder. Go to the Tyke Content folder. Then Content, Notebooks, MAST Summer Webinar 2026. The second Spectra session for Spectra, and then this SDSS Stellar Spectra notebook. Thomas, can you post that path in the chat just in case anybody couldn't follow along?
Can do.
Thank you very much. But yeah, once you navigate there, you should see this Jupyter Notebook open, which you will be able to follow along our tutorial. One more thing, make sure in the top right corner here that you are on the Tyke Python kernel and not Python 3. The Tyke kernel will have all the packages that we need already installed for you, so that will just make things a little bit easier. So I'm going to make sure that is selected. But today's session is all about spectra, the rainbow connection. We're going to learn how to classify spectra and to do multi-mission searches with MAST, looking for data from Hubble, James Webb, and the Sloan Digital Sky Survey missions. So by the end of this webinar, you will be able to learn how to use astroquery.mast to search for multi-mission data in the MAST archive. Astroquery.mast is our Python package for searching and downloading all the data in the MAST archive. We have a lot of data for you to download. We also are going to understand how to download and plot a stellar spectrum using MAST and astroquery. And then we're going to learn about spectral classification and how to classify different types of stars based on the appearance of their spectra. So without further ado, let's get started. For the introduction, the Mikulski Archive for Space Telescopes, or MAST for short, is an astronomical data archive that contains data from over 20 different missions, including all of these featured in this graphic here: HST, JWST, TESS, Roman, and many more. We have over 400 million astronomical observations. We have images, we have spectra, we have light curves, catalogs, any type of data you could possibly want for astronomy. MAST is the place to come looking for it. But for this webinar, we are going to focus on spectra. So the idea behind a spectrum is if you take a light from a star or a light bulb or any source really, and put it through a prism, you get a lot more information out of that light. So instead of just getting the overall brightness of the object, you get brightness as a function of color or as a function of wavelength. And that can tell you a lot about a star or galaxy or many different astronomical objects. For example, you can tell what temperature it is with the knowledge that kind of red things tend to be cooler than blue or bright things. If you compare like a welding torch of very bright blue light to the light from your stove, which is more red, it's that kind of idea. You can also learn a lot about the star's chemical composition through the absorption lines and emission lines in its spectra, and even about its age and evolution history. So those are some of the things that we're going to talk about today. To get started with this tutorial, we need to import a couple of statements or a couple of packages in Python to help us out. We are going to be using NumPy for basic math and array handling. We're importing a few things from matplotlib for making plots and creating figures of our spectra. We're going to be importing AstroPy to open the files that we download and work with them. And then finally, we're going to import astroquery.mast, which is the main Python package for searching and downloading data from MAST. So this is the most important one that you should remember from today. So let's go ahead and run this cell, import all those packages successfully. And then this cell just updates some of the plotting parameters, makes the font sizes bigger, things like that, so that the figures are a little bit easier to see. So we're going to run that as well. All right, let's jump into it with the first section of our webinar, which is about searching MAST with astroquery. I have each of these sections, I have a little poem or a little song verse related to spectra. So the first poem here is from Kermit the Frog, who played at the World Cup this weekend, if you guys saw that in the halftime show. But Kermit asks the very important question, why are there so many songs about rainbows and what's on the other side? And that is what we are going to be exploring today. Why spectra, why rainbows are so important for astronomy. All right, so the easiest way to search for spectra in MAST is to use astroquery.mast, which we are going to demonstrate in this cell here. I'm going to start it running while I explain, just because it takes about 30 seconds to a minute to run usually. So I'm going to get it going now, but astroquery.mast is a Python package for searching all of the data collections available at MAST. The main function we're going to be using today is called query criteria, where you can query, the MAST archive for many different things based on your criteria. So you can search by coordinates, you can search by target name, you can search by mission, you can search by cameras or instruments. Query criteria is a very powerful function that searches all of the data, all of the missions in the MAST archive in a single query. So in this example, we are going to search for JWST spectra, James Webb Space Telescope, using these keywords in this function. First, we have obs collection, which searches by mission name. So for this example, since we're interested in the James Webb Space Telescope, we are going to search for obs collection equals JWST, as we did here. For data product type, is how you can limit the search to certain types of data. So if, for example, if you're interested in images only, you could use image as your data product type. But of course, today is all about spectra, so we're going to be looking for spectra or spectrum. And then page size and page are these two extra parameters to limit the size of the result. So this query, we're basically asking for every spectrum that JWST has observed in its 5-year mission so far. And as you can imagine, that's a lot of data. So we're using page size and page just to limit the size of the query to the first 10 results and getting the result from there. And you can see our cell has finished running. We have queried the archive for all JWST spectra and returned the first 10 results. This is a table that tells you a lot of metadata information about each of these observations. A couple of important columns here. We have obs collection, which is the mission or the telescope that was used. We have the instrument name, so the camera that took this observation. For most of these, it's NIRSpec for JWST, which is the near infrared spectrograph. We have filters or grading, which tells you the name of the filter, as well as the wave region here. JWST is an infrared telescope, so all of these are infrared spectra. And some other information as well that you might want to know, like target name. These are the names of the galaxies or stars that were observed by JWST. You have the coordinates, RA and DEC, and you have some timing information. So when were these observations taken? So yeah, that's the basics of writing a query for a MAST. You can search the archive, return all of the observations, and get some information to help you find the data that you want. And then here I just have some information on the returns in the table as I just described. So that's how you search for all JWST spectra in the archive, but let's try a little more targeted search next. Let's say I want to find a spectrum of the star LHS 1140. This star is very exciting. It was in the news just earlier this week because it has an exoplanet, and that planet was recently confirmed to have an atmosphere. This was the first Earth-like planet that we detected that has an atmosphere other than our own, and so that was a very exciting discovery that happened this week. This planet was, or this atmosphere was just detected with JWST data, but let's say we want to find the Hubble spectra to go along with this star to learn more about the host of this planet. No, I don't know the coordinates of this star off the top of my head, but you can find them using astroquery. So if we use observations.resolve object function, and type in the name of the star, astroquery will resolve this target name to coordinates using a different service in the background like Simbad or NED, and it will retrieve the coordinates for us. So I can run this cell, and it will tell me the coordinates of this star are an RA of 11 and a dec of about -15. And this works for any object you could possibly think of. If you want to know the coordinates of the Crab Nebula, for example, you can do that. Or if you want to know the coordinates of Tau Ceti, which is a star that was featured in the recent Project Hail Mary movie, you can do that. And these are the types of things you can do to search for data within MAST if you don't know the coordinates of the star off the top of your head. But I'll move back to this exoplanet hosting star for the rest of this example. So now that we have the coordinates, we can search for spectra of that star using the same format that we did previously. So we have the coordinates using resolve object, and now we're going to use that query criteria function, which we did before, to search for the coordinates and for data product type equals spectra. So this will search for all data in MAST from this star, and then in this block here, I'm just printing all of the missions that we have data-wise. So I'm going to run this. And I will also mention that you can use the keyword object name instead of coordinates if you'd like. So object name does the resolving behind the scenes for you as part of this query. So you could skip a line and not ask for the coordinates, but just query based on the object name directly if you would like. But we can see that there's quite a lot of data for this star in MAST. We have spectra from HST, the Hubble Space Telescope. We have 200 different observations, and from the James Webb Space Telescope, we have 6 observations. So both HST and JWST have observed this star. And if we want to see some more of those options, I can just print the results as we did before and see the big table of data. We have a bunch of JWST observations, HST observations in different filters, different instruments. For Hubble, we have the Space Telescope Imaging Spectrograph, or STIS, as well as the Cosmic Origin Spectrographs, or COS, and both UV, optical, and infrared wavelengths of this star. So now that we know what observations are out there, let's try downloading some. So let's say we're interested in the Hubble Space Telescope spectra for this observation. We know there's about 200 of them. We don't want to download all of them, but for Hubble, a very good options for spectra is the Hubble Spectroscopic Legacy Archive, or HSLA, which is a really great resource because it combines data from multiple different observing programs into a single spectrum for each target or each star. So if you don't want to download all 200, you can just download this one spectra, which has combined all of those spectra conveniently into one file for us. So we can filter by provenance name equals HSLA, or the Hubble Spectroscopic Legacy Archive, just for this star. So we're going to redo our query here, searching for LHS 1140, and we're looking for provenance name equals Hubble Spectroscopic Legacy Archive. And it returned one result. So we have one HST observation, which combines data from both the Cosmic Origin Spectrograph and the Space Telescope Imaging Spectrograph from a whole bunch of different filters. It ranges from the ultraviolet to the infrared wavelengths, and more information that we have here. So this is the observation that we want. Once we have that, we can download it using the get products list function in astroquery. So this function will tell you exactly what files are available for this observation and list them all for you to look at. So if I run this cell, you can see that there are 24 different individual files as part of this observation. There's a lot of different options here. Some of them are just preview images, so like PNG images, which show you the overview of the spectrum. Some of which are text files or logs about how the observations went or how this spectrum was created. But the main ones to look for are things flagged with minimum recommended products in this column. These are the default files, the recommended products, the ones most useful for science that have been flagged by data scientists or the people who made the observations or otherwise. There's quite a few here, but the one that we're most interested in is this ASPEC file, which, as you can see in the description, here is a HSLA co-added and abutted spectrum for multiple gradings. So these CSPEC files, these co-added spectra files, are each just for one filter each, but this ASPEC file combines everything into one file, so that is the easiest one to work with if we want a complete spectrum. So yeah, a lot of files here. Most of them aren't important for the sake of this tutorial. They're preview images, calibration files, things like that. But the ASPEC is the one that we are interested in. So we can download that one by filtering for ASPEC and this download products option. So observations.download products, we're passing it the list of products we just created, and we want the ASPEC file. So if I run this cell, you will see that it is downloading this ASPEC file for us, and it has completed. So if you've been following along correctly, you should have downloaded this one spectrum file for this star, and I can run this cell to see that indeed we have this file now in our directory to work with. Okay, that's the end of the first section, an overview of how to query data in the MAST archive. So now we're going to do a interactive exercise. You're going to build your own query. So for those of you who are following along in Tyke, I will give you guys, let's say 5 to 10 minutes, somewhere in there, to write some code for yourself. The idea is that we want to query a star based on these coordinates. We're going to look for the OBS collection SDSS. So instead of searching for Hubble or James Webb, we're going to use the SDSS mission, which I will tell you more about in a bit. We want to limit the results to spectra using data product type and using radius of 0 to limit the search radius. That guarantees you only get this star and not maybe a nearby star or something like that. So it's a 3-step process here. You're going to query MAST using query criteria. You're going to retrieve the available products using get product list. And then finally, we're going to download the spectrum using download products. So yeah, I will give you guys about 5 minutes to work on this, and then we can go over the results. You can also type done in the chat when you're done, and if enough people have indicated that they're ready to move on, we can move on early. But I will let you guys go at it for a bit. Good luck. Okay, if you weren't able to finish, no worries. I will go over the solution now so you can follow along and type in your own code. So the first step to search MAST spectra of this star, like we did before, we are going to use the observations.query criteria function. We need to pass it a few things. First of all, our coordinates. Just going to copy and paste it from here. Up next, we need to give it OBS collection to search for only the mission data that we are interested in, which for this exercise is SDSS. Up next, we need to give it the data product type, which of course is spectrum today. And then finally, radius 0 to look for only targets at that coordinate. So that's part 1. We can see I made a typo. It's observations, not observation. But we can run this cell to see what results we have. Taking a little bit, doesn't usually take this long. There we go. So we see there's 2 results. So we have 2 spectra of this star for SDSS data. Up next, we can retrieve the products that we have available with observations.getProductList. And see what products we have there. So there are a total of 12 files here. Again, we have preview images, science images, things like that. Most of what we're not interested in, but this minimum recommended products column will get us the main file that we want. So we can download those using observations.download products. We're going to give it the products list. We want flat equals true, which will just download it into the current directory. and MRP only equals true to only download those default main files. And so here it's downloaded those 2 spectra files for us for this star. And that's the solution for exercise 1. I'm going to pause for a moment if anyone has any questions before we move on to the second part of the notebook. All right. So now that we have our spectra files, we've downloaded 2 spectra from SDSS and 1 from the Hubble Space Telescope. Let's learn how to plot these spectra and see what they look like. We are going to unweave a rainbow, as the poet John Keats said. So a little bit more intro about the Sloan Digital Sky Survey. So in the first exercise, we downloaded a spectrum from SDSS. SDSS is a huge international collaboration that's been going on since about 1998, and it has observed millions of stars, galaxies, and quasars through a telescope that's located in New Mexico, the United States. And we now have all this data available through MAST to download. SDSS has images, it has spectra, it has catalogs, it has many different types of data, but on the spectra side, one of the sub-surveys of it is called the Sloan Extension for Galactic Understanding and Exploration, or SEGWAY, which has provided optical wavelength spectra of about 400 stars in the Milky Way galaxy. So this is a good library if you're interested in looking at different types of stars. And there's a couple links in here as well if you're interested in learning more about SDSS and the data available at MAST. So let's take one of these spectra that we just downloaded and plot it to see what it looks like. So the first step to opening the file is with AstroPy. We can do fits.open and pass it the name of the file. And then we can use the file.info to display some basic information about the file and what it contains. So we can do that here. It tells us the file name, and it shows us that this file has 10 different extensions as a FITS file. The first extension, the primary header, just contains mostly metadata information, so things about when and where the observations were taken, what telescope was used, what day it happened on, and so on. COAD, the first extension, is going to be the main one of interest today. That's the COADed spectrum, the final processed, analyzed, and fitted spectrum from SDSS. You also have the SpecObj table, which is the second extension here, which contains a bunch of measurements from the spectrum mostly. Things like its temperature, its chemical abundances, things that you can pull from the spectrum. And then the rest of these B and R number extensions are the raw data, so before the data was processed from the blue chip and the red chip on the instrument, but we don't need to worry too much about those. So that's what the different extensions are in this file. So let's take a closer look at the actual spectrum extension, the first extension here. We can do that by just printing the column informations that are in the spectrum. We see, first of all, flux, which is one of the 2 things we need for our spectrum, so that is important. The next one is log lam. Lam is short for lambda, which is the symbol used for wavelength. So this is the wavelength in log space for us. IVAR is the inverse variance. It's basically the uncertainties in the spectrum, if you're interested in that for your science. And the rest are various quality maps and models for this spectrum. So we can plot the spectrum using these columns. Basically, we just need log lambda for the wavelength and flux for the flux. And we're also going to be plotting the model here, which is the best fit model spectrum, and have all of those together. So to make our plot, we're first going to initiate the plot. We need to specify what wavelength and flux we want for our spectrum. So for wavelength, we're using the log lambda column, and I'm raising it to the 10th power to change from log lambda into just lambda or just linear space. And then we're going to plot the flux and the model spectrum as well. To plot, we just use matplotlib plt.plot, plotting the wavelength versus the flux in gray, and then the wavelength versus the model flux in black. And the rest of this is labeling our axes and plotting the legend and so on. So we can go ahead and run this. And we have our first spectrum from this file. This star I chose for this tutorial specifically because it's a star a lot like the sun. So this is very close to what the sun spectrum looks like, actually. You can see that we have flux on the y-axis, or brightness is the way you can think of it, and wavelength or color on the x-axis here. The star is brightest in the kind of 5,000 angstrom area, just like the sun, so it's kind of peaks in the green color, but it is pretty bright across all wavelengths here. We have this kind of smooth black body continuum in the background, and then all of these big dips in the spectrum. These are the absorption lines or features which are created by different elements. This one right here around 6,500 is probably the most famous absorption line, hydrogen alpha, created when an electron jumps from the second shell of hydrogen to the third. And all of these different lines correspond to different elements and different chemical compositions as well. So these two deep ones over around 3,900 are from calcium, for example. This one in the middle here is from sodium, I believe. But yeah, these absorption lines are something that astronomers are very interested in learning more about the chemical compositions of these stars. So this is what the spectrum of a star like the sun looks like. But all different stars have different spectra, different chemical fingerprints, different appearances for how their rainbows look like. This was really first discovered in 1912 by famous astronomer Annie Jump Cannon, which you might have heard about in your introduction to astronomy classes. And she developed a method to classify stars based on the appearance of their spectrum. This classification system is still used today to classify stars and do a number of science. In her scheme, stars are classified by a letter according to the appearance and strength of absorption lines in their spectra. So a star can be either O, B, A, F, G, K, or M based on this system. Our star is a G star, our sun is a G star, as it turns out. And we'll be looking at all of these different kinds of stars today, so you can see what their different spectra look like and how to classify them yourself. Luckily, one of the things about SDSS, they have done all the hard work for us and already classified the spectrum, which you can read directly from the file. So if you look at the SpecObj extension, which is that table that contains measurements, which I mentioned earlier, you can pull out the classification directly just using the subclass keyword. So this tells us that this spectrum is a G2 spectrum, which is the same type of star as our sun. All right, so that's the first spectrum. Up next, let's see what another spectrum looks like. Let's take this HST spectrum, which we downloaded earlier in the notebook of LHS 1140, and plot that one next. I've started the exercise here by opening the file, printing some basic information about it, and pulling the wavelength and flux out of the science extension, the main spectrum for this case. And so your task for exercise 2 is to plot the spectrum like we did before using matplotlib, plot the wavelength versus flux, and see what type of star this is. So I will give you guys another 5 minutes to work on this. So go ahead and go have fun, go at it, and we'll see what it looks like after that. Like before, you can post in the chat when you're done and ready to move on. Okay, let's go over the solutions then. So we have our wavelength and flux, and we just want to plot the spectrum. So the easiest way to do this is plt.plot with the wavelength for the x-axis and the flux for the y-axis. And we can just plot that first of all and adjust the plot from there. So we can see our spectrum here. It looks a little funny. The y-axis is a little bit off based on some instrumental effects, maybe bad pixels, I'm not sure, but we can adjust that pretty easily using the y-limit option for the plot. So let's go from 0 to, I'm just eyeballing this, maybe about 0.2 to the -12 based on what I see in the plot. And that looks good. I can adjust it a little bit more, make the limit a little bit shorter, and maybe go a little bit into the negative here. I need to go that far. There we go. How's that? Yeah, so here we have the plot as well. Like before, we can label the axes so we know what we're looking at. And add some grid lines to it. And we can see this is what the spectrum of this star looks like. which is quite a bit different from the spectrum we looked at before. The sun-like star that we plotted earlier is brightest in green and has these like big hydrogen lines and other elements in it. This spectrum looks completely different. It is brightest in the red, so this is a very red star, and it has these huge absorption lines. It just has thousands and thousands of features that are all piling up on each other, some of which are made by molecules, these big bands here. And it almost has no blue light or purple light at all. It is a very orange and red color star compared to a star like our sun, which has light across all of the spectrum. So yeah, this is just two examples of two very different types of stars and how you might classify them. Any questions on that? Okay, up next, we're going to enhance the plot a little bit. So a spectrum is a rainbow, so let's enhance this plot by adding some color to it to kind of mimic what you would see out of this spectrum if you were to see it with your eyeballs instead of just looking at it as lines on a graph. So I've defined this function here, which is going to add a rainbow background to the spectrum based on how bright the flux is at each of those wavelengths and the different absorption lines. I'm not going to go over this in detail. All of the code is here if you want to look at it yourself. But for now, I'm just going to run this cell to define this function. And then I am going to replot our SDSS spectrum of the sun-like star using this extra plot rainbow background function to see what it looks like to our eyeballs. This will just take a second to run, and now we have this. This is the same plot we had before, except the spectrum is plotted in white instead of black now, but we have wavelength versus flux for this STSS file, and I've also put the classification of this star on the plots. This is a G2 star like the sun. And hopefully the rainbow background gives you more of a feel for what this actually looks like in practice instead of just the numbers on our instruments. But yeah, we have this whole sweep of rainbow colors. We have these big black bands in the spectrum where the absorption lines are, so that's where the brightness goes down, caused by these different elements. And in the case of this star, it is brightest in the green and faintest in the red and purple ends as the spectrum goes across the different wavelengths. So yeah, we can see how the spectra correspond to different features in the lines. All right, so using this, the next section, we are going to make an atlas of sorts so we can classify stars for ourselves. So we've seen two examples so far of very different looking spectrum. This HST spectrum of a pretty cool red star, and then this spectrum from SDSS of a sun-like star. And so for this section, up next, I've curated a list of one type of spectrum for every type of star. So the anti-jump cannon classification system of O, B, A, F, G, K, M, and I've thrown a white dwarf in there as well for good measure. But these are just different SDSS observation IDs for each of these stars, so we can create an atlas, a reference to use for classifying stars. So I'm going to run this cell. This next function builds on everything we've learned so far as well. This just queries MAST based on these observation IDs for each of these spectrum, so we can get the products and download these files. And once we have this function defined, we are ready to make our plot of everything. I'm going to start running this cell while I explain it because it takes a second. But yeah, what this cell is doing is it loops through all of the stars in our star list, which we defined here, each of these different types of stars. It is downloading the spectrum using this little helper function that we wrote. It is opening the file. It is plotting the spectrum, the wavelength versus the flux. We're adding that pretty rainbow background from the previous section, and then making some other labels and such on the plot. So this does take a second to download each of the 8 stars in our example here and to plot the example, but any second now, it should pop up. And there it is. So this is a big figure, and it's basically our reference for different stellar classifications. So for each of these spectra plotted one on top of the other, we have the wavelength versus the flux, as we did before. for different types of stars. So this is an O star up top, the hottest kind of star. You have an OB star next, white dwarf. I've ordered these by temperature, so the hottest star is at the top and the coolest star is at the bottom. And you have the OBA, FG, KM, everything in between. And so with this figure, you could really see what the different types of spectral classes look like. From the hottest stars, really don't have any absorption lines. They're hot enough that all hydrogen atoms are ionized, so there's no electrons to fly around and create absorption lines, or at least very few. As you get hotter, you get these big hydrogen features in B and A stars. A is where they're most strongest, so all of these big lines here are the lines from the hydrogen atoms. The white dwarf has very strong hydrogen lines, but the lines are actually quite wide. They're quite broad. In that case, that's because the white dwarf is small and rotating quickly. And then you get into stars like the sun, like G stars, as well as cooler stars, FKM, which not only have hydrogen lines, but also lines from a bunch of other different atoms like calcium, sodium, iron, and the like. And then finally, we get to the coolest stars, which are very red and have huge absorption features and big molecular bands in them. So yeah, this is a very pretty plot, a quick way to learn about different types of spectral classifications. So let's do a quick exercise using this. Let me have it open in another window right here for reference. And let's scroll back up to our HST spectrum here. And based on the appearance of our HST spectrum and our little reference guide here, what type of star do you think our HST spectrum is? Post it in the chat when you have an idea. Looks like M4 on the bottom. Yes, exactly right. Yes, so this is an M star, much like this cool example on the bottom, and we can tell because it has a lot of red, it's brightest in the red, and it has these big sweeping molecular band features. So in this case, this is a red dwarf star, a star a bit smaller and cooler than the sun, but it has these planets around it as well. So yeah, stars come in all shapes and colors. All right, we can scroll back down here. All right, for the very last exercise of this webinar, your task is to classify a random star. So for this exercise, we're going to put together everything that we've learned so far, how to download spectra from MAST, how to plot the spectrum, and how to classify stars using this reference guide, and go from there. So to start, we're going to just pick a random star. So this cell is going to query SDSS data. It's going to pick one random star out of the first 100, so with this numpy.random choice, and then it will show you which star you have been selected, which one you've randomly rolled for the last exercise. So you will probably get a different star than I do here based on the nature of random selection. And then for the last 10 minutes of this webinar, we're running a little bit short on time, so maybe, yeah, just for the sake of time, I will do this live and you can follow along with your own star if you would like, just so we make sure to finish on time. But once we have our random star, just thinking about. All right, so we have this star. In this case, the star is named SDSS 3298549248. Just a phone number of a star based on its coordinates. Yeah, we're going to go from there. So you will probably have a different star than I do, but we can query MAST to download these products using the observations.get product list function that we did before and pass it my random star. To see that. So we see the different type of files available here. We can download those using observations.download products. pass it the products list, give it flat equals true, and MRP only equals true, since we're only interested in downloading that Spectrum file. Can do that, and now it has downloaded this file star here. Up next, we can plot the spectrum. I'm going to cheat a little bit and just go up here to where we plotted one earlier. Right here, I'm just going to copy and paste this code in the bottom and give it the right spectrum file that we just downloaded, which is named like this. And we need to open it with astropy.fits. And we've plotted this random spectra. Easy as that. So this star, we can see, looks a little bit different than the other two. And so the last task is to classify it. Yours might look different than this, depending on which random star you did, if you're following along. But I can look at these side by side and try to guess what kind of star this is based on the guide that we have on the left. So for my star, I'm going to guess maybe it has these big feature right around 5,000, which I see in like the F and the G stars. But it's also fairly cool. So the sun kind of peaked more around 5,000, whereas this one's more around 6,000. So I'm going to guess this is either like a G or a K star based on this observation. And then we can find out what star it actually is using the file, the spec.obj table as we did before, and the subclass column as so. And if we print that, it's telling us it's a K3 star. So I was right. It is between a G and a K, this nice star, a little bit cooler than the sun, but not as cool as the HST spectrum we did. So yeah, hopefully if you've been following along, you have now classified your own star using this guide and this plot, and you now know everything you need to know to do science with spectra at MAST. You've learned how to download spectra, to search the MAST collections for what we have, how to plot the data, and how to classify stars based on their spectra. So I just wanted to end with this poem from Rebecca Elson called We Astronomers, which is, we astronomers are nomads, merchants, circus people, all the earth our tent. We are industrious, we breed enthusiasms, honor our responsibility to awe. But the universe has moved a long way off. Sometimes, I confess, starlight seems too sharp. And like the moon, I bend my face to the ground, to the small patch where each foot falls. Before it falls, and I forget to ask questions and only count things. So I hope you take this as inspiration and motivation to not forget to ask questions, and look at spectra, learn how to use them, and but appreciate the beauty in the data as well. So thank you everybody for coming. There will be an office hours next week, a week from today, if you have any other questions or want to talk to us more about how to find spectra at MAST. And there is also one more session as well on August 18th, which is going to be all about catalogs and catalog queries with astroquery. So if that sounds interesting to you, we hope to see you there.